well, Eta Earth, the sort of fraction of Earth-like planets around Sun-like stars has now been constrained, even if there's some uncertainties. This is not the complete story, right? This is only telling us how many planets are more or less in the habitable zone and have a size that is more or less similar to the Earth. But there are many other properties we'd like to know if we want to fully characterize an exoplanet. And some of these are accessible through remote sensing, so observations from the ground or from space, but others are not and require a more complete understanding of planet formation and planet evolution. Luckily, today, we have a fairly complete theory for planet formation. So you've all seen plots like this before, right? You form a disk out of a collapsing molecular cloud. This disk evolves on a timescale of a few million years, and ultimately planets form, leaving a planetary system after the disk dissipates. And for the planet formation itself, so sort of how to go from microscopic dust that is present in the ISM to larger bodies and ultimately planets, there's now also a fairly complete picture in the sense that there's a series of steps, right, like dust coagulation, streaming instability, pebble accretion, etc., without any holes necessarily in that story. And this picture is pretty flexible as well in the sense that by changing the efficiencies or the timing of different processes, it can explain also different types of planets, right? So for example, this figure, I forgot to include the reference, I'm sorry. This is from Meach and Raymond's review, I think this year or last year. By forming, for example, your initial planetesimals inside or outside the snow line, you can end up with Earth-like planets or gas giants. And if you add migration to this picture, this framework becomes pretty flexible and can explain some of the things we've been seeing with Kepler, for example. On the other hand, it's not developed enough to allow us to make really concrete predictions, right? We cannot start from a specific disk structure and predict exactly what types of planets will form. And the other way around is also true. We cannot look at a planet and then go back and say exactly what the disk was like, where it formed. So we need to improve on this picture. So with that in mind, I want to sort of start at the beginning here today, and then we'll see how far we get in an hour. But the goal is to sort of walk through some of these steps and use carbon and observations of carbon as sort of a guide to tell us what's going on in nearby disks. So at the beginning, right, we think disks are formed from molecular clouds in the ISM.
This carbon thing, remember?
Hey, Lucy.
Yeah.
So you'd expect them to inherit sort of the elemental abundances that you find in the ISM. So for example, 1 in every 10,000 atoms or so is a carbon atom, and the dust to gas ratio is typically about of order 1% in terms of mass. And of that carbon in the ISM, about...
So where do you get the dust to gas ratio?
This one? Well,
is that for carbon, or that's just in general?
No, that's the total, all the refractories. Okay. You can add the ISIS if you want, change it by a factor of 2 or so.
Okay.
Yeah, this is just solids to gas in...
and all the elements together.
Yeah. Yeah. Okay. And for the carbon, typical numbers, though they can vary a bit, it's like 50% of the carbon is in refractory. So this can be carbon-rich grains or long carbon chains frozen out on grain surfaces, and the other half is sort of in CO or CO2.
It also could be in fullerenes, and this is what we wanted to do for the grant proposal that Daniel submitted, but he didn't think it was relevant. But you know, they say that 50% is in grains because they see a gas phase depletion studying atomic lines. But if it were in carbon nanostructures and not grains, which are somewhat different beasts, that could account for the depletion.
Yeah.
Yeah.
Yeah, sure.
We don't know.
Yeah, I'll be focusing mostly on this other 50% that's in CO and CO2 for now. But I'll get to the refractory carbon later.
Okay, great.
As an example, for the sun, the elemental carbon abundance relative to hydrogen is also in this range, like a few times 10 to the minus 4. In disks, though, this number seems to drop, right? So if we start out with our 10 to the minus 4 CO abundance for the ISM here, this ratio plummets by like 2 orders of magnitude in a few million years. And this is a plot from a recent paper by Coco that Canberra was also on. And I'll spend a lot of time discussing how this plot came about and how we can use it to learn something about planet formation. So we'll come back to this a few times. I want to start with TW Hydra. So TW Hydra, of course, is a big, bright, nearby disk. We can resolve it well. We have beautiful images of different CO isotopologues, scattered light, millimeter-sized grains with ALMA. But what we have to remember is that all these tracers or all these observations are tracing a slightly different part of the disk, right? So the scattered light is coming from the surface. The solids that ALMA can see are in the midplane, but a bit further out. And the different gas phase carbon reservoirs are tracing different layers in the disk. But connecting these observations to each other and to the main sort of mass reservoir, which is cold gas, or to the planet formation, terrestrial planet formation zone, is not necessarily straightforward. So for the picture I'm presenting today, may be more relevant than these nice spatially resolved observations is this observation from by Ted Bergen showing HD emission from TW Hydra. So this is now the disk integrated line that gives you an independent measure of the molecular hydrogen mass in this disk. And you can compare this to similar observations for CO isotopologues. So these are generally more optically thin than regular 12 CO. So they should be more representative of the total amount of gas phase CO. You can compare the two and find that the CO is indeed depleted relative to the ISM value by about 1 to 2 orders of magnitudes. With a small caveat that you're still not tracing gas that is cooler than like 20 something Kelvin. So you're sort of seeing this warm molecular layer here and inferring that the CO is depleted by 2 orders of magnitude. Similar results were obtained by Mikkel Kama. He was fitting simultaneously, again for TW Hydra, the SED, a bunch of CO lines, the HD here, and some atomic carbon lines, and also found that it's necessary to reduce the elemental abundance of carbon by 2 orders of magnitude. So if we add this asterisk that says, okay, this is in the sort of 20 plus Kelvin region, we can put TW Hydra on this plot here.
So I have a question about the depletion.
Sure.
Relative to H2, right?
Yeah.
How is H2 determined?
With the HD line. So
HD, okay, that's what you were showing in the, okay. So they must assume a D to H ratio though.
Yeah, that's a good question. I think that's fairly well constrained, but I would.
You know what?
Yeah, there's probably people.
I'm curious, yeah.
Yeah, I can look that up and get back to you.
Okay, thanks.
For most regions, though, or for most disks, we don't have access to this HD line because it's hard to see, and it's you need to be in the far infrared, and we currently don't have any instruments to see it. So I'll illustrate what is more typically done by looking at the Lupus star-forming region. So this is a bit younger, a few million years. This is work by Megan Ansdell. So on the left, I'm showing disk-integrated fluxes for 13CO and C18O. And then on the right, these are resolved sub-millimeter ALMA images. And what you can do then is you can compare these fluxes to predictions from models that assume that in the warm molecular layer, you still have this 10 to the minus 4 ISM-like CO abundance. There's yeah, this is a complicated story, but you can use the models like this to infer total gas masses for all these individual disks. You can get an idea of the total dust mass by converting the ALMA images, the flux to a sort of pebble mass, assuming you know the temperature of the dust, the opacity, things like that. And then you can compare these two to calculate the total disk integrated gas to dust ratio. Now what you find is that first of all, these gas masses are generally pretty low, right? They're sort of around or below a Jupiter mass, which is surprising if you think these disks will still form planetary systems. And also the gas to dust ratio is fairly low. It's around 10. So there would be a dust to gas ratio of 10%. Yeah, which is surprising because when you start out with 1%, so you think, well, forming planets will put solids into bigger things, so you would expect a lower dust to gas ratio rather than a higher one. So there's two ways out of this. This is a great plot made by Camber. One is that sort of, okay, maybe that's correct. Maybe the gas to dust ratio is indeed really small, reduced by a factor of 10 from the ISM, and maybe this is pointing to something like gas dispersal, photoevaporation, something like that. Alternatively, you could say, well, no, I don't believe that. I think the dust to gas ratio should be fixed to this magical 1%, and instead we'll interpret this as being again depletion of CO relative to H2. So these disks are still fairly massive in terms of their gas, but it's just the CO that's missing, which is why these models that assumed an ISM-like CO abundance yield low gas masses. So motivated by the results for TW Hydra with the HD, and also by this point that actually the dust masses, if you multiply them by 100, seem to do a better job of explaining the accretion rate onto the star that you can measure separately. Seems to me that the more obvious choice is the second one. So the disks are not depleted in gas, it's just the CO that's missing. And that's also the interpretation that Coco and others used in this work. So if you use this 1% dust to gas ratio, you can put Lupus and Chameleon 1 on this plot as well. Younger systems are a bit harder because they tend to be embedded still. But Coco again used this time the NOEMA interferometer to observe 3 systems, TMC1A, HL-tau, and DG-tau in different CO isotope logs. And by using this last one, which is the most, I guess, optically thin one, for which it's most obvious that the emission is coming from the disk, she was able to model these systems, or reproduce these lines. These are, again, disk-integrated fluxes by using, or finding that sort of a pretty normal CO to hydrogen ratio is enough, right? So these young sources appear to still have this ISM-like ratio, and then on the timescale of a few million years, this number plummets. So the question is then, yeah, what is going on, and is this related to any planet formation processes or not, which is, of course, happening on similar timescales. So one idea to get rid of the CO is just through chemical processing. So using gas phase or grain surface reactions, you can destroy your CO and put the carbon in either methanol, methane, CO2, or other hydrocarbons, depending on the density and temperature, I guess, locally. Camber studied this process for a whole grid of models with different disk temperatures and different cosmic ray and X-ray intensities, as well as for different dust grain size distributions. So on the top here, most grains are small, and at the bottom there's a bunch of big grains. And this plot is then showing the CO abundance again in the warm molecular layer at 100 AU after 1 million years, right?
Sebastian.
Yeah.
Sorry, I got a bit lost.
Okay.
My understanding is that it was only right. The HD was only for HL tau, the HD measurement. So how else is the CO to H?
Right. So
CO being measured?
the HD is only for TW Hydra.
So how are we
there's
getting
actually two other disks that I don't mention here. I think GM Tau, and there's one more where this has been done. So there you have an independent measure of the molecular hydrogen gas. All these other points hinge a little bit on the assumption that the dust to gas ratio is 1%. So
that
then
could
you
be
use the
wrong.
dust.
Okay, so that's being assumed, not confirmed.
Well, it's being assumed, but these models fit things like they don't just fit the dust. They fit the SED as well, and they reproduce features seen in scattered light. So it's assumed, but it's constrained in a way as well.
And you were showing line profiles. Is there a way the line profiles confirm the CO to H ratio?
Right. So these are models for
work?
different CO to H ratios. Right.
But
so
I don't understand how you model these. Oh, with different. You're just modeling a CO abundance, right?
Yeah. You take your best guess for the temperature and density structure for a disk that comes from fitting the SED and looking at the dust. You put in CO at different mixing ratios. So for example, here 10⁻⁵, 2 × 10⁻⁴, 8 × 10⁻⁵. Then you do a radius transfer model to figure out what the line flux will be for that disk. And those you compare to the observed profiles.
But when you model line profiles, you're just basically getting a CO abundance, right?
Yeah.
And everything else is assumed.
Yeah.
Yeah, okay.
But I mean, you could argue based on this plot that the dust mass seems to be an okay tracer of what the gas is doing, right? Carlo Manara, they tried to find the similar correlation by comparing the mass accretion rates onto the star with the gas masses inferred from CO, and then you don't find anything. It's just a scatter plot. So it seems to be that the dust, at least for Lupus and some of the younger systems, is a fairly good tracer of the total gas mass, or at least a better one than the CO fluxes tend to be. Yeah.
Okay. Yeah. Thanks. I just I wanted to be clear on whether those what those line profiles were giving.
Yeah. Sure.
Thanks.
Yeah. Right. So back to Camber's plot. So this figure then shows that unless the disk is really warm, you can get about an order of magnitude depletion of CO just by local chemical processing, right? Getting the 2 orders of magnitude that we saw in the previous plot is tricky. Plus, this processing seems to not really work if you have a significant amount of grain growth, or if you remove some of the water in the disk, which apparently is what's going on if you look at Michiel Hoogheid's paper, for example, for TW hydrants. If you remove water and this oxygen from the gas, this processing of CO becomes hard. Yeah, so there's a few reasons to believe that the chemistry alone has a hard time to reproduce this plot.
But I have another question. Why would carbon chemistry be significantly limited by the water abundance? Because certainly in carbon-rich circumstellar envelopes, where the C to O ratio is definitely in favor of carbon, you get a lot of chemistry going on.
Yeah, I think the difference is probably the temperature. So these regions are pretty cold, right? So it's somewhere between 20 and 30, 40 Kelvin.
That's the temperature of the external part of a circumstellar envelope. And that's where you get a lot of these hydrocarbons. These and branch chains and all kinds of things.
Yeah, so the formation of hydrocarbons is included in these models.
And how well are the rates known for these reactions?
Oof, I would have, so this is where I point back to my first slide and highlight that I'm presenting other people's work, and I'm not super comfortable with all of it, but maybe at the end camera can answer that.
Okay, thank you.
Excuse me. Thank you, Lucy and everyone. I know this is really, there were a lot of questions, but we need to stop, end this meeting sharp at 1 o'clock. So I think it would be great if Sebastiaan could finish the talk, and then could you write down the questions so that they could,
Because I bit off more than I can chew, and I hope to get to the end. So
yeah, thank you.
I'll speed up a little bit.
Yeah,
so the other
questions to the end. Thank you.
Yeah. Or send them through the mail. Physical mail, no emails.
Sounds like our president.
So the other process that can contribute is sort of a combination of dust coagulation and dynamics. So we know that as grains grow in disks, they tend to settle to the midplane, right? So where small grains can sort of move up and down because of turbulence, large grains typically are confined to the midplane regions. So if there's a region in the disk midplane where the temperature is cold enough for CO to freeze out and be removed from the gas, you can potentially hide some of the gas phase CO in this midplane. It can act as a sink because your solids are sort of accumulating this ice and they're just sitting there, so there's no way for the CO to come back. Of course, grains don't just settle. Once you form sort of pebble-sized particles, they will tend to move radially as well and drift inward on fairly short time scale. So as they drift through the snow line, which is at a few tens of AU, the CO ice they're carrying can evaporate again and be returned to the gas. So sort of intuitively, you would expect to see these regions of depleted CO in the molecular layer and enriched or enhanced CO inside the CO midplane snow line. And of course, I just want to highlight that pebble drift is not just a theoretical construct, right? We see for example, in the Lupus disk sample I showed earlier, it's clear that most of the millimeter dust disks are significantly smaller than the gas disk. And also for TW Hydra that I discussed, if you put the ALMA continuum map on the CO map, you see that the dust is really pretty concentrated. So this drift is something that we really think is happening. So I've been trying to model this. I start out with a pretty boring disk with most of the CO or most of the carbon in CO. It's frozen out in the midplane, which gives you this 10 to the minus 4 CO abundance in the molecular layer. And then I run this model for a few million years, and I include different combinations of either just the chemistry or chemistry and things moving around, or dust coagulation and chemistry and various mixes of all of these. And for the chemistry case, for example, this reproduces the results from earlier works like Camber's paper, even though the chemical network I'm using is very simplified. But what you see here is that after 3 million years, you can process the CO in the cold regions, right? So you form methanol here and CO2, but in this warm molecular layer, where temperatures are a bit higher, it's hard to process this CO. Most of the pathways are just too slow to operate at a few million years. If you include everything, this depletion is more dramatic and sort of in line with the observations. We can get up to 2 orders of magnitude in a few million years. And the reason is that it's this combination of two processes. One is that you're mixing CO down and processing it here on the grain surface, or you're mixing it down, sticking it on a grain that then grows larger and just sits there and act as a sink. We also see that for the two models, these two models on the right-hand side that includes pebble drift, you see this enhancement of CO inside the snow line that I talked about earlier. These are just the same models, but now plotted in a vertically integrated sense. So you see indeed that in the warm molecular layer, this complex model with everything sees these 2 orders of magnitude depletion, and you see this bump in the inner disk. But I guess just generally, this plot is showing that different combinations of the physics and the chemistry give very different radial profiles for your CO depletion or your CO abundance. So it's interesting then to go back to some of these disks, especially the bigger and the brighter ones, try to get radially resolved observations, and from these try to deduce what the radial profile of the CO depletion pattern is. So this is what Coco did last year on a paper that Canberra and I also contributed to. So it's DM Tau, HT163, IM loop, and TW Hydra. You take these models, fit them together with the SED using all kinds of fancy codes, and you can find what the CO depletion factor is, so the number by which it's different from the ISM as a function of radius. Now, for most of these disks, the spatial resolution is not good enough to see the region inside the CO snow line, which is sort of indicated with this arrow here. But for HT163 it is. And there seems to indeed be this bump with an elevated CO abundance inside the snow line. So this is interesting. And otherwise the numbers, the order of magnitude for the depletion factor is sort of similar to what I saw in those models on the previous slides. For HT163 in particular, Coco did follow-up work using, again, the NOEMA interferometer, and was able to show that this orange sort of model for the radial profile, which is based on the ALMA data, indeed does the best job of reproducing some of these profiles. And this model compares, this is the orange line here, compares fairly well to the models I published these observations. Well, this curve inferred from observations matches my theoretical prediction from a year earlier fairly well, although it wasn't designed necessarily for that disk, so we wouldn't expect necessarily good agreements. And you can use then this excess in CO to figure out what the total pebble flux has to have been that has drifted through the CO snow line, which in this particular disk is 70 AU. And for HT163, Coco and collaborators find that you need a pebble flux of about 15 to 60 Earth masses per million years, which is sort of in line with fluxes that sort of generic disk models tend to get. And just to put it in context a bit more, modern models that try to reproduce the solar system, gas and ice giants, find that for this intermediate regime where the cores are growing mostly via pebble accretion, you need something like about 100 Earth masses per million years. So this is a fairly comparable flux. And by the way, if you think this is weird to start forming Jupiter at like 15 or 20 AU, you should check out Guy and Obrecht's recent paper arguing that actually forming Jupiter's core exterior to the N2 ice line helps resolve some of the questions that were sort of asked after the latest Juno measurements. Okay, so this is cool. We can look at gas phase CO and try to figure out what the pebbles have been doing, when did they form, how did they drift, what was the drift, what was the radial flux. And this is important for many planet formation aspects, right? So first, as these pebbles drift in, at each successive snow line that they pass, they will shed some of the ice, right? CO will go first, CO2 later, methanol, water. So if you compare a model with significant pebble drifts or without pebble drift, these plots are complicated, but I'll try to make the point clearly. If you compare giant planet formation models in disks with significant pebble drift or without significant pebble drift, you find that the giant planet atmospheres that form here are typically enriched in C2H and O2H because you have this enhanced CO and CO2, these abundances in the inner disk. And also getting C2O ratios larger than unity, these green points here, you can only achieve this in these models with significant pebble migration. You don't see these here. Pebble drift flux is also important for terrestrial planet formation. This is showing a plot by Michiel Lambrechts doing simulations of planet formation in the sort of inside the water snow line with different pebble fluxes reaching this inner disk. Right? And again, these numbers are quite comparable to the ones that were constrained by Coco and others. So if you have a small amount of pebbles reaching the inner disk, you form these boring sort of embryos, sort of Mars-sized embryos. If you have more mass coming in, you can form something that looks like the solar system. It's kind of hard to see, but each line is sort of one model realization. And if you increase the flux even more, your cores will grow so quickly that they can migrate through you expect them to migrate through the gas disk and sort of pile up here. So you can form these sort of super Earth-like systems. So it's interesting to try and contrast this to some of the architecture seen by Kepler, but I don't have time for that. So taking a step back, before you can form planets, and after you have formed your pebbles, you need to first form planetesimal size bodies, right? Objects of like 100 kilometers in size. And the preferred method now is the streaming instability that Andrew discovered and sort of, really described, worked hard to describe well. So the idea is that in a particular region of the disk, you have an elevated pebble concentration or pebble abundance, and the feedback onto the gas then triggers this strong clumping, which allows you to gravitationally collapse pebble clouds directly into planetesimals. But the big unknown here is where and when in the disk can this actually work? Where can this happen? With some models predicting planetesimal formation only around the water snow line. Also, Johanna's work is showing sort of planetesimals only forming between a few AU to maybe 10 AU, and in a relatively narrow window in terms of time. While other models predict you can form planetesimals everywhere in the disk over sort of millions of years. So this is a big open question. And one way to address this maybe could be that in these models I presented earlier, these have been constructed to match the gas phase abundances, but they also predict the abundances of the pebbles growing in the midplane, right? So for example, after, I don't know, a million years, my pebbles that are sitting here are composed of this mix of water and CO and CO2. So it would be interesting to try and compare this to constraints we have on planetesimals in the solar system and elsewhere. So in the solar system, there's a couple of regions where we have planetesimals, right? Where planets didn't quite form either because it was too busy there, they were being perturbed by Jupiter, or maybe there was not enough mass out here in the Kuiper belt. And we can go sort of through these. So for comets, I don't want to spend a lot of time on comets, but typically they have like maybe 10% CO relative to water ice, and a 1% of methanol and other species. And in a very cool paper recently, Christian Eistrup tried to compare constraints from, 15 comets to his local static astrochemistry code, where he evolves a solar nebula forward in time to pinpoint sort of where and when each individual comet formed. And what he found is that basically everything was consistent as long as the comets were forming in a region sort of close to the CO ice line, which in his model starts around 30 AU and then slowly moves inwards. So by looking at comet compositions, you can try to figure out where and when they formed in the solar nebula. But of course, comets are sort of complicated, different sizes, they really evolved, they come close to the sun a bunch of times. So, who knows what's happened to them. So maybe a more direct comparison can be made to the Kuiper belt, and in particular, the cold population of the Kuiper belt. So around 45 AU, in the cold classical Kuiper belt, there's planetesimals sitting there that we think formed in situ and haven't really been disturbed since. They're on low eccentricity, low inclination orbits, so they don't come close to the sun and are always sitting there in this cold outer region of the solar system. Now, because they have low eccentricity orbits, they're hard to study because they never get close to us. So if you want to study one up close, you have to actually launch a spacecraft and sort of fly out to see them, right? So this is what New Horizons did. Launched in 2006. They had a flyby of the Pluto system, I'm sure you've all seen. And then in January 1st, 2019, it arrived at this object here, which is now known as Arrokoth and used to be, I guess, MU69. And this is the first sort of cold classical Kuiper belt object studied up close, and it's the furthest object, I think, in the solar system or anywhere that has been visited by a spacecraft. So it's quite cool. And I guess, first of all, the structure of this thing is very consistent with the formation via the streaming instability and gravitational collapse, right? It's two lobes that are that simulations reveal must have come together at a velocity of only a few meters per second, even though the escape velocity, the escape velocity is similar, but the local typical collision velocity you would expect for unbound objects is orders of magnitude higher. So these two lobes probably were gravitationally were in orbit around each other when they formed. Also, the color is very sort of smooth across both surfaces, so it's consistent with the two lobes forming from the same pebble clouds. And New Horizons was able to get infrared spectroscopy of the surface. So the spatial resolution is not great, but Will Grundy and others tried to sort of look for changes in the two lobes or changes in the spectrum of this crater or outside the crater, not really finding anything. So it seems to be it seems to be made out of the same stuff. But the spectrum was surprising in the sense that it revealed methanol features here around 2.3 micron, but there was no clear sign of water, or anything else really. So CO, nitrogen, things like that, while those are present on the surface of Pluto, you don't expect to see them here because this object is too small to hold on to them. But water we would expect to see. So it's sort of surprising that they're not there. So what I can then do is can go back to my disk model with the chemistry and the pebble coagulation and all that included, and ask sort of what is the composition of the pebbles growing at 45 AU, and how does it vary in time? What I find is as well, it's initially sort of, these are just my initial conditions, right? There's lots of CO water. There's this period after a few million years where the methanol to water ratio is quite high. So we can try to think about, because we know Arrokoth formed at 45 AU through the collapse of a pebble cloud. I think trying to connect the pebble compositions to the Arrokoth compositions is sort of interesting. But of course, these results depend a lot on what I assume in my model. So if I change the cosmic ray ionization rate, for example, make it really low, there's no chemistry. If I make it too high, there's only a very narrow and early window for forming your planetesimals. So,
sorry to interrupt for a second. Should the x-axis really be million years there, or should it be years?
Wait a minute, you're not allowed to interrupt.
Yes, this is a million years. Well, clarification
allowed
questions.
To interrupt.
I'll take the clarification questions. This is years, obviously.
Oh, so we can ask clarification questions.
Yes. Yeah, so this is work in progress. Moving beyond the solar system, there's of course debris disks all around, right? So these are gas pore systems, hundreds of millions of years old, that have rings of planetesimals that are colliding and producing debris, right? So small grains that you can see with Hubble, and millimeter-sized grains you can see with ALMA. And in some of these systems, gas has been observed, CO gas. Not in these beautiful spatially resolved images, but if you sort of integrate over the azimuthal angle here, or in HD 181327, you find that there's this CO emission peak that is co-spatial with where the dust is sitting. This is then thought to be CO, second generation CO, that is produced during the collisional cascade, during the destruction of these planetesimals, as they release their CO ice back into space. So this has worked for these two objects, and Luca Mata and others have then, by using the models that connect the dust production rate to the CO production and destruction rate, have been able to tease out what the sort of total CO and CO2 masses are of these planetesimals, right? So for formal hot, this is the picture is consistent with maybe a few tens of % of the planetesimal bodies being in the form of CO and CO2. And for HD 181 it's a bit lower. You can compare this to comets in the solar system. Right? So yeah, this is quite interesting. And it's showing us that we can get constraints on planetesimal compositions, not just in the solar system, but also exterior, which I think is really, really exciting. Of course, every now and then, turns out one of these exo-comets visits us in the solar system, so that's even easier. We saw Oumuamua and Borisoy, of course, and I haven't read these papers in detail. We discussed them at the group meeting, but I have to fully digest them. But I guess both papers that looked at comet Borisoy with either ALMA or HST seem to suggest that it's a very CO-rich object, much richer in CO than any of the solar system comets, except for this one. But that one is weird. So this is pointing then to a formation far outside the CO ice line. But I guess compared to the models I showed earlier, it's also pointing to a formation that's sort of early in the sense that there hasn't been enough time for chemistry to process the CO and put it in something else.
What is the evidence for high CO?
Right, it's these, it's from the ALMA, it's the comparison of the CO flux and the HCN flux. And from the HSD, I think it's UV, CO and UV, something like that. Yeah. As I said, I haven't really digested these papers, but I can send you the links if you're interested. Okay, so
thank you.
Yeah, I'm close to maybe getting to the end of my talk, but not quite. So at the end, well, just to recap, sort of, I think 10 years ago, I always thought that sort of when thinking about planet formation, we have information about the dust and the planets, and then in between it's just a guess. But I guess nowadays that really isn't true. We have quite a diverse range of constraints on planetesimal compositions, both inside and outside the solar system. I think that's pretty cool. So we should try to sort of leverage that and build a story there. But at the end of the talk, I want to talk about Earth for a little bit. So, of course, carbon is important for the Earth, right? This is me, basically. I think most humans are sort of 18.6% carbon. So it's clearly important for us as carbon-based life forms. Carbon is important for setting the temperature through the carbon silicate cycle, things like that. And then, of course, this is caffeine. So, right, we wouldn't be here without coffee, I guess. But even if carbon plays such an important role for life on Earth, it's actually really underabundant, right? So from this chart I showed early on, you would expect, maybe since the Earth formed close to the sun, where CO and CO2 cannot exist as solids, you would expect maybe to hold on to this 50% of the 10 to the minus 4 C2H. But actually, when you compare the Earth abundance of carbon to the solar abundance, it's depleted by something like 4 orders of magnitude, right? And you see this depletion in meteorites as well, but it's not as extreme as in the Earth. And this point here is representing the bulk silicate Earth. So I guess that's everything except for the core. And okay, maybe you can hide carbon in the core, but yeah, from my reading of the literature, which hasn't been very extensive, I guess that's fair. But it's unlikely that you can bridge these 4 orders of magnitude. So something has happened somewhere during Earth formation that got rid of the refractory carbon. So what could that be? One idea that borrows some of the concepts that we discussed already earlier during this talk is to have oxidation or photolysis of refractory carbon in the surface layers of the disk, right? So at 1 AU, in the midplane, it's not quite warm enough, most likely, to get rid of refractory carbon on the grains. But high up in the disk, temperatures are above like 4 scale heights in this particular model by Lucia Klarman. You can actually do it. So if there's enough time to sort of through this turbulent mixing to mix all your small grains up once to get rid of their carbon before you can form the planetesimals that later end up forming the Earth, you can maybe resolve this issue. So these are then model runs by Lucia showing the carbon fraction of the grains as a function of time. This is the initial condition, and then the black is after, I guess, 1 million years or so, both from oxidation and photolysis. And the top panels are showing local models. So these are 1D vertical disk models. And what you can see is that, I guess together these processes, with photolysis being more efficient in this particular model, I'm not sure why, you can get rid of a couple of orders of magnitudes. However, if you include pebble drifts, so if you include pebbles coming into the inner solar system from a bit further out where this process is not so efficient, this doesn't work. Yeah. So if you want to destroy if you want to get rid of refractory carbon on the grain surface, you cannot have any material coming in from the outer disk. And you can try to tie this then to this other story from Kuiper et al. And also Steve Tesch's work, that seem to find that you need Jupiter's core to form early, within or around 1 million years, to separate in space these reservoirs that will eventually end up forming the carbonaceous and non-carbonaceous meteorites. Right. So maybe if Jupiter forms early, you can get into this upper panel and still get rid of some of the carbon. Another solution is to have sort of transient heating events where even the midplane around an AU gets warm enough to sublimate some of the carbon. So almost there, but as a bonus, I'm glad I didn't run out of time. I want to talk about white dwarfs because I think this is super cool. So when a star dies, right, a fairly low mass star, it leaves a planetary nebula and a white dwarf. And some of these white dwarfs, like this one, have a debris disk around them. So this is the SED for this particular helium white dwarf, showing a belt of material, I think at around 80 AU, so quite far. So this is stuff that used to be a planetary system, or maybe still is a planetary system, who knows, and then sort of survived the death of this the central object. Now in other systems, not this one, but in other systems, you can observe in the spectrum of these white dwarfs, you can observe metals, I guess, in the astronomy sense, that shouldn't be there, because they can only survive for a fairly short amount of time on the surface before the high surface gravity sort of sucks them up into the center of your white dwarf, and you don't see them again. So by comparing then removal rates for these different elements, you can build up, for example, for this single white dwarf GD40, you can build up pie chart for what the composition of the material is continuously falling onto the white dwarf, which in this case is mostly iron, magnesium, silicon, rock-forming elements. You can compare that to, so the details depend a bit on what you assume for the mixing in the white dwarf photosphere and blah, blah, blah. But you can compare these numbers to the Earth and the chondrites and Comet Halley. And what you find in this case, and actually in almost all cases, is that the material that's being accreted by these white dwarfs is really Earth-like. So like 90%, 95% of the stuff is composed of oxygen, like rock-forming elements. Nothing really looks like a CAI-like planetesimal or extremely carbon-rich planetesimal with the carbon, like silicon carbide or whatever. You don't really see this. Everything is Earth-like. And also, if you plot the carbon abundance, it falls sort of here, right? Orders of magnitude below the sun. And I tried to guess where the Earth would be. I figured it would be sort of around here. Tried to make the symbol bigger, so it had a larger chance of being in the right spots, but sort of over there. So yeah, this is somewhat surprising to me, right? Because this picture here is sort of suggesting that to form a carbon depleted Earth, you need Jupiter to form early and block the drift of pebbles and blah, blah, blah. But there's not that many systems that have a cold Jupiter at a few AU. So that we're always seeing these Earth-like compositions for materials falling on white dwarfs is maybe kind of surprising. I don't know. If you have any ideas, yeah, I'm interested to hear them. So I guess to sort of wrap this up is that, yeah, I've been showing mostly observations, I think. I'm a modeler myself, but I guess the conclusion is that there's hope, right? There's all these cool observational constraints from sort of every different phase of planet formation. So I think, yeah, if we really want to connect the sort of disk physics to planetesimal formation, pebble migration, planet formation, yeah, I think there's still hope, but I don't see exactly how to do it. I guess we have time, so that's okay. Yeah, and with that, I guess in the last 5 or 10 minutes, I'm happy to take any questions.
All right, thank you, Sebastiaan. Okay, so for questions, please use the raise hand feature. That's the blue hand under the participants list, and then the organizers will call on you. All right, I see a question.
Yeah, and
from...
we can leave. Well, I'm not going to end the meeting at 1, so keep going as long as people are interested in talking too.
All right, question from Larry Nittler.
Thanks, Kimber. Great talk, Sebastian. Quick question on your last point about the exoplanets. If you could go back a couple of slides.
These?
Yeah, I think maybe one more. Actually, no. This one is good.
Okay.
One thing from the, one thing about those white dwarf ones pointed out is that chondrites themselves are also very depleted in carbon relative to bulk solar.
Right. They're sort of over here.
Carbonaceous chondrites too. So none of those photolysis and models and things, they all show, even if they work for depletion, it's only in the sort of 1 AU region, not out at 6 AU or something where the CCs might have formed in the DESH model or whatever. So is that important?
Yeah, that's true. So if you, so I guess your point is that we should worry about not just about reproducing bulk silicate Earth, but also the chondrites and the carbonaceous chondrites. Yeah, that's fair. I think this the answer is will likely be a mix of either this processing in the surface layers mixed with vertical transports, or transient heating events close to in the inner disk, and then mixed with sort of outward transport some way. Yeah, I'm not completely sure about what dominated when, or to what extent that combination of processes is unique to the solar system or should be the same somewhere else.
Yeah. Thanks.
Question from Ben.
Thanks, Sebastian, for a great talk. I have a quick question. You mentioned that the measurement from a CO is we can only probe until about 20 Kelvin. So I wonder, how much do you think that how much CO can be high within the temperature below the 20 Kelvin region?
Yeah, that's okay. That's a good question. So sort of hidden in one of these plots. Here. So the reason you can't see CO in colder parts of the disk is just because it freezes out, right? So if you ignore the chemistry completely and only focus on transport and freeze out, you get into this picture here. So here, I've been able to hide about 90% of the carbon the CO that was originally here is now sitting in the midplane, just by vertical transport and condensation on larger grains. Now, when I say 90%, it's you have to remember that even though that you're removing 90% of the CO up here, you're not adding that much mass to the midplane, because the midplane anyway is much more massive than the surface layers. So the sort of the fractional amount by which the CO mass in the midplane increases is almost negligible, even if you remove 90% of the stuff up here.
Okay, thanks.
Okay, Lucy.
Yes, Sebastian, I was curious about your point with the Helix nebula. You said that the white dwarf showed, just looking at atomic transitions from elements falling onto the white dwarf, that carbon is depleted?
Right, so not for the Helix one. I just wanted to show a pretty picture. I don't think the Helix white dwarf is polluted, but about 25% of the white dwarfs you look at will have this pollution in on the surface, and you can identify a whole bunch of lines. I think.
Sure, I understand. Yeah,
and so most of these are depleted in carbon. Yeah, if you plot it like this. So this is carbon to calcium and iron. Right?
Okay, so but that doesn't necessarily mean carbon is depleted throughout the nebula.
No, that's right, and that's so a tricky part. Let me phrase it differently. The nice part about for example, looking at the Kuiper belt or looking at the planetesimal belts in debris disks, is that you know where they are now, and you can more or less figure out where they formed. This here, all you know is that there's stuff falling onto the white dwarf, and whether that's a disrupted planet, a big asteroid, or whether it came from 1 AU or 2 AU. That's kind of hard. That's kind of hard to say. Yeah. You can look at other elemental abundances. So you can look at sort of ratios between, I guess, like lithophile or siderophile elements to see trends that look like core formation and things like that. So you can see that it's material that underwent some sort of differentiation, just like it happened in the inner solar system. But to match it to an actual formation scenario or a location can be quite tricky. Yeah. Also the amount.
Go ahead. No, it's just very interesting that we've been studying molecules in planetary nebulae and measuring, CO to H2 ratios. And, in the gas in the nebula, it's about 10 to the minus 4 CO to H2. So it seems like the inner region has had some kind of elemental depletion, if what you're saying is correct. I don't know what nebula you've looked, what you've plotted here. I'd be curious. Right.
Yeah, this review by Juan Young is really great. So you can.
Yeah, that'd be very interesting to look at.
But yeah, it's obviously a completely different reservoir. You're looking at solids after planet formation compared to the gas in the ASO. Yeah.
Thanks.
Yeah, right. Just to add, sort of maybe the total mass you need to pollute these white dwarfs is really tiny. I think for this one, it's like maybe one asteroid is enough to produce these features.
Mm-hmm. Okay, question from Vladimir.
Hi.
Hey, Vlad.
Hey, how are you doing?
Good.
Yeah, I was wondering here. So, interesting what you said, and I can see that there are many ways to remove CO from the gas phase. But one thing that I was wondering is that the assumption, right, that is made about the CO to H2, and you're using HD to measure the H2, right, as was asked before. Now, the HD line stops very high up in the atmosphere, right? It is quite awfully thick. So do you know if the CO and the HD are measured at the same height? Because that high up, you're not constraining mass, right? The disk has,
so it's a very good question. So, first of all, again, none of this is my work. So I'm not constraining anything, but this is the plot from Fava et al. Showing sort of where in the disk the C18O and the HD emission comes from, just to illustrate that it's sort of co-spatial. And I think my understanding is that the HD usually comes from a bit deeper in the disk, especially if you're outside of like 20 AU, and that optical depth effects are more important sort of closer in, but that's not the region that the CO is tracing anyway. So even though both these lines are not necessarily tracing the coldest gas in the outer disk, they are tracing a sort of similar-ish region, and that's why you can use them to map. That's why I added this sort of clause here that you're only probing the sort of gas above 20K. Now, if you're interested in it, I would point you to either this paper by Leon Topman or Mikkel Kama. Leon looked at these lines in TW Hydra again with sort of new models, and Mikkel looked at 15 other upper limits for HD detections in disks to try and get upper limits for the mass. They have really nice plots showing exactly what the vertical and radial region is where the HD is coming from. I think both lines, the 1.0 and 2.1, come from slightly different regions. So yeah, I guess you're right. You need a good thermal model for your disk. But I think these models are fairly well developed. So I would point to those two papers.
All right, and then we have a question from Daniel.
Sebastiaan, very nice talk. I have one question about, I'm wondering about all the disks that you showed, especially TW Hydra. And so I was wondering, and HD 163296, so these are pretty unusual objects, right? So you kind of compare the younger objects with a few old objects, and of course, this can be interpreted as a temporal evolution in properties, but we know that TW Hydra and HD163, they are outliers, and probably they are really not representative. They may be 1 out of 1,000. So I was wondering whether we have what is our thinking about why TW higher is different from the younger disks or the typical disks at that age, and whether that process can it be linked to actual chemical composition? Can it imprint the chemical composition?
Yeah, that's a good question. So I think the reason why these disks, even if they are maybe unusual and not necessarily representative for disks of 10 million years old, were included in this particular plot is just because of the nice constraints that we have, right? For TW Hydra, there's the HD, and for HD163, there's this nice spatially resolved observations of CO isotope logs. But when I drew this sort of arrow here, I tried not to draw it through these disks, because you're right, they're not the same temporal trends. I think what's important to point out is that all these processes, like the CO sequestration in the midplane and the chemistry, they depend very sensitively on the temperature structure of your disk. So HD163 is pretty warm, and that makes both of those processes less efficient, right? Because in order for you to have this sink in the midplane, you need a very cold midplane. So if you don't have it, you can mix your things vertically all you want, but you will never really deplete the surface layers. And same with the chemistry. I showed the figure from Camber illustrating that the CO processing is very slow if you have a warmer disk. So it's not surprising to me that the depletion is not clear. It's not clearly evident for 163. TW Hydra, yeah. Honestly, I don't know. I mean, I'm more comfortable connecting the models I'm doing to these early disks, because all my models include is dust evolution up to sort of pebble sizes. Anything after that is not included. But there have been some works that I think by Melissa and McClure and Miguel again, that try to constrain the atomic carbon to hydrogen ratio in the material that's accreting onto the star, or that's present in the really hottest inner parts of the disk. So then you have sort of another data point. You can see what's being removed in the outer disk, and then planet formation, I don't know. And then you can see what comes out at the other end, very close to the star. And I think if I remember correctly, most of those observations seem to point also to a carbon depleted inner disk. So somewhere along the way, things are locked up either in larger bodies or or are trapped behind gaps, right? We've seen from D-sharp that there's all these pressure bumps and gaps and things like that you have to worry about, I think, for the older disks.
Thank you.
All right, do we have any final questions for Sebastian? Lucy, do you have another question, or is that your raised hand from before?
I think she's on the phone.
Oh, okay.
Yeah, sorry, I got a phone call. No, that's my raised hand from before. I can talk to Sebastian offline. I got a lot of questions, but.
All right.
Good.
Thank you.
Time for a very.
So there is one, Camber Denton mentioned something in the chat window.
Oh, okay.
He wasn't sure whether we know how thick the primary graphic crust was. Larry Nittler would be called the estimate, and he said he gotta go. But since this is recording, I thought I'd mention that.
Wait, what was the question again? I don't.
In the group chat window. It's about graphitic crust thickness.
Yeah, I can see the chat, but so I guess he's asking about for the Earth, maybe, right? So how representative the bulk silicate Earth is for the whole planet, or how much carbon can you stuff in the core, something like that?
Yeah, the silicate, I guess, since there was talking about crust. Or silicate.
I thought the questions was what about Mercury? As Steve is saying in the comments, yes.
Oh, right. Is Mercury
yeah
on that plot? Oh yeah, it's not on here. I think the constraints are not as good, but So in Ted's 2015 paper, there's an extended version of this figure on the right here with, I think, Mercury and Mars and possibly Venus also on there. I think generally they follow this trend, more or less. I'm not sure exactly what happens here, but I think they are consistent with the whole inner solar system being all the solids in the inner solar system being carbon poor, and not just some special process happening to the Earth. But yeah, I have to read this paper again.
All right. I think that's going to be it for this talk. Thank you to those of you who stuck around. And thank you once again, Sebastian.
Yeah, thanks for coming, everyone.
Yeah, and we will see you next week.